from this example, I think what we still didn't mention about is in the MATLAB, they compute the value of the gain. They compute the value of the gain k. When we just click a cursor along the locus of the root that plot by MATLAB, the program will display the gain k for that location of the root. without the MATLAB, or how to say, without the MATLAB, how can we obtain that value of the gain k? Or what is the background program of the MATLAB that compute the gain k along the locus of the root? If we have a root locus, and we may have three pole. Three pole can be everywhere, but in this case, maybe we consider one pole on the real axis, and another two are the complex conjugate. Of course, the first thing we should plot the root locus first. The first step, we should plot the root locus first. Maybe this gonna correct or incorrect, I'm not sure, but we should use our previous step to identify the position of the pole, the zero, find the asymptote, and the direction of the asymptote. We need to do it first. And we sketch the root locus. And at one point on the root locus, if we want to know what should be the gain k, at that point of root along the locus, how can we find the gain k? When we pick any arbitrary point along the root locus, how can we find the gain k with respect to that point? We begin from the characteristic equation again. And we know that we can rearrange the gain that relate to the minus of 1 per gs, when gs is the open loop transfer function. So the magnitude of gain k, you know that magnitude k can be the positive value, and the magnitude of gain k is the magnitude of 1 per gs. What does it mean by 1 per gs0? Actually, gs, transfer function gs can be something like s minus S1, S minus S2, S minus S3. If the system in the characteristic equation, if they have maybe three pole, each pole gonna have their numerical value, and in the general form of S, it can be in this form, but GS0 means we replace the general S by S0. S0 is the point that we want to find again K. S0 is the point that we want to find again K. And GS0, you know, S1, S2, S3 is the pole location, and pole location are fixed. But S0 is depend on you want to find again K somewhere along the locus. It should be along the locus. It cannot be somewhere else outside the locus of the root. So you need to plot the root locus first and then pick the point along the locus, and you solve for the value of the K. In order to confirm whether S0 is along the locus or not, you should review the angular criteria. From previous week, previous class, and the next step is straightforwardly 1 per magnitude of the transfer function. Consider S at S0. It's straightforwardly. So not sure. Let's try with one example. For example, if the, let me see, I think we should try this example again. When we have the pole at 0 and -4 plus and -4j. So it means we have the open loop transfer function equal to 1 per S and S plus 4 square plus 16. In this case, we're gonna have pole at 0, pole at -4 plus 4j, and pole as -4 minus 4j. We're gonna have three pole. And we can plot the pole on the S plane. Pole may be on 0, -4 plus 4j, and -4. And we already plot the root locus for this system. It may be something like this, right? Maybe something like this. And maybe if we want to replicate this, GS maybe need to be written in the terms of the factor of the root something like this. And if you pick one point S0 here, if you pick one point S0 here, and you want to know the gain, if you want to know the gain, at that point, the gain can simply be obtained by substitute S by S0 and consider the magnitude. And just consider the magnitude. And here is the idea. How can we find the gain value of a root at a specific point on the locus? How can we apply this in the application? Let's try with this example together. The open loop transfer function of the system. And we're gonna vary the gain K. And the root gonna change the location along the locus. And we need to decide P control. We need to decide P control by adjust the gain K, and the system need to have the damping ratio 0.9. And the last point, minimum time constant, means the system should be as fast as possible, but still have the damping ratio 0.9. We should begin by plot the root locus of this system. We have the 0, -3. We have pole. And we plot the root locus of this system. You know that when we draw the axis of the S-plane, in our class, maybe it should be better for us to have a bigger space on the left-hand side, because we mostly consider stable system. When the value of the real part is negative. The real pole at 0, the real pole at -2, and the 0 is at -3. When we see this, what's gonna happen? There are two poles. When the gain is equal to 0, the location of the root is exactly at the location of the pole. When we increase the gain, the locus will hit with each other and then create the breakaway. And then it's gonna come back and have the break in. After they have break in, one root will go to the 0, another one will go to -infinite. Why I know this? Because we have one 0 and we have two pole. We have 1, 0 and we have two pole. The asymptote gonna be asymptote gonna be 180 degree. 180 degree. We have only one asymptote, which it makes sense because we have two pole and one zero. One root will approach the zero. Another root will go along the asymptote at 180 degree or go to the minus infinite. The problem now is where is the break away and where is the break in point? Where is the breakaway and break in point? Why we should know the breakaway and the break in? We want to know the radius of this circle. We want to know the radius of this circle because we want to pick the point on the circle. We want to pick point on the circle that relate to the damping ratio 0.9. Damping ratio 0.9. We see this and the damping ratio, the constant damping ratio line is the radial line drawn from the 0, 0, the origin. And another thing that important is the angle that the constant damping ratio line make with the horizontal axis, the negative real axis. The cosine of this angle is equal to the damping ratio. Cosine of this angle is equal to the damping ratio. And when we come back to here, if we need to find this angle, we know that the cosine, the angle here and here are different, okay? Different in meaning. This is the angle of the asymptote, but this is the angle of the constant damping ratio line. Cosine of the angle, okay, let's just make it different. Normally they use the phi, but yeah, cosine of the angle is equal to the damping ratio. It means the angle is the arc cos of the damping ratio. By the calculator, maybe it's about 25.8 degree, maybe the angle. So if the system, if we pick the gain K, and the system still have the desired damping ratio, we may have two possible values because a constant damping ratio line cross the circle with two intersections. At gain K1 and at gain K2, it crosses the circle at two intersection points. But the second requirement is we want the minimum time constant. Minimum time constant means the system should be as fast as possible. If we have two solutions between K1 and K2, the value on the real plane is minus psi omega n, and the value on the imaginary plane is j omega d. The fast system, the minimum time constant or the fast system should be this solution. If the system is very far to the left hand side from the imaginary axis, the system gonna be fast system. But if the pole is close to the imaginary axis, the system gonna be slow. So for this design, we may prefer K2 with relate to S2 somewhere on the circle that intersect with the linear line, the constant damping ratio line. Before we find the intersection, at least we should find the equation of the circle. We begin from the break in and break away. Break away and break in point from d by ds of -1 per gs equal to 0. So it means d by ds of, yeah, we're gonna ignore the minus sign, right? And we're gonna switch numerator and denominator. So s plus 2 divided by s plus 3, or d by ds of s squared plus 2s divided by s plus 3 need to equal to 0. The dip of the fraction, again and again, we maintain the denominator and we dip the numerator. Then we maintain the numerator and we dip the denominator. We have now it seems like we have the break in and the breakaway point. It seems like we have a circle that have the center at the 0 and -3 plus square root 3 will be the breakaway, and -3 minus square root 3 gonna be the break-in point. It seems like we have a circle with the radius of 0.3, a circle with the radius of 0.3, and the center of the circle is at -3. If we need to draw equation for this circle, it may be, yeah, x plus 3 square plus y square equal to the radius square. Is the equation for the circle, this circle. I consider this x and this is y. And For the line, the constant damping ratio line, the equation for the line y equal to minus tan of the angle multiplied by the horizontal value minus x tan. So we just need to solve this equation. And how to solve this equation? Yeah, we may begin from x squared plus 6x plus 9 plus x squared and tan of the angle equal to 3. I already like when I solved this equation, I found that x equal to minus 1.37 and another value is minus 3.67. The meaning is the real part at this first intersection and at this second intersection that relate to K1 and K2, that relate to the K1 and K2. At K1, the real value of S1, the real value of S1 and the real value of S2. But we want the fast system, right? We want a fast system. So we're gonna pick K2 and S2. We're gonna pick K2 and S2. We are not going to select K1 and S1 because the system gonna be slow and small time constant. Actually, the time constant is 1 per sine omega n. If we want the big time constant, or if we want a small time constant, sine omega n should be the big solution, the big one. And at S2, the real part is minus 3.67. And imaginary part is obtained from the relationship by the damping ratio. Maybe you will try to cross check, but when I did calculation, the real part minus 3.67, imaginary part with the damping ratio 0.9, I got 0.6. But what you can see is the real part is big, but imaginary part is quite small. The damping ratio is big, it's almost 1, and the angle is very small. So it makes sense that the angle is small. It makes sense that the imaginary part is not that big, and the system not gonna extremely vibrate. The last step we need to do is the gain K. If we need to find the gain K, The gain k is 1 per magnitude g of S0. G of S0. And S0 means this one, the S2. The S2. The gain k at this point. And we need to come back to the open loop transfer function. We need to come back to the open loop transfer function. 1 per G open loop magnitude. 1 per G open loop magnitude is equal to, you know, S2 and S2 plus 2 and S2 plus 3 magnitude. That's it. That's it. I can draw it here. Magnitude of S2 multiplied by the magnitude of S2 plus 2 divided by the magnitude of S2 plus 3. And when you solve the magnitude of this, you're gonna get the gain k. The gain k that make your system have the damping ratio 0.9 at the minimum time constant. After you solve for the gain k, you may try another similar problem. How about when we need a maximum time constant? Maximum time constant. If you want maximum time constant, you need to pick K1 and S1. You need to pick K1 and S1 instead. And K1 and S1. S1 has the real part minus 1.37. What should be the imaginary part? And what should be the gain K at that point? Here is the analytical way. Of course, we have the MATLAB tools. MATLAB tool is very easy. We take the same open loop transfer function. We compose the sys by transfer function of num and then. And the transfer function give the same value, and you just use the Locus sys. We cannot draw a constant damping ratio line on the Locus plot in MATLAB, but we can slightly move the point along the locus so that we can see the damping ratio 0.9. You see that along the locus, we have two solutions that relate to the damping ratio 0.9. We have two solutions here. If you need minimum time constant, you're gonna pick the fast solution. If you want the slow system, you're gonna pick this solution. And you know, they also show the frequency. That means the system is fast or slow. High frequency is fast, and same damping ratio, so same percentage of the overshoot. They also show the location of the pole, the location of the pole. The location of the pole compared to this one is slightly different, slightly different. You see, minus 1.41 compared to minus 1.37, minus 3.45, minus 3.67. So I think my explanation to this is maybe our assumption here is the locus perform an exact circle. Actually, this is my personal assumption. Maybe it's not a circle, or maybe we have some mistake when we try to compute the sine and cosine of degree angle. And this numerical value is not exactly the same. Not exactly the same. But as I mentioned, when we compare the gain between K1 and K2, the locus move from the first pole and hit with the locus that come from the second pole, and then go up, go down, and go along the locus, So at K1, for a slow system, we need the gain K just 0.8. But when we still continue increase again, at 4.8, we achieve this requirement again. Here is the last example for today. We are going to design a PD control by root locus method. The system, the plant, have the transfer function, and we also have the sensor transfer function. And PD controller, KP plus KDS. The technique that we are going to do now, chord, pole, zero, cancellation. Pole zero cancellation means we're gonna pick the zero in the PD controller. That's gonna cancel with the pole of the plant. I'm gonna compose the PD gain by S plus 1, which means KD equal to K and KP also equal to K in this case, and I pick only one K. Pole zero cancellation means now the open loop transfer function. Gonna be controller gain multiplied by the plant gain and the sensor gain. Now the the open loop transfer function gonna be k multiplied by s plus 1 multiplied by 200 divided by s plus 1 s plus 10. Pole 0 cancellation means we can reduce the complexity of the system. But this technique is very dangerous. It's very dangerous. How dangerous it is? The original system here, it seems like we have pole at 0, at -1 and -10. Why I decide to cancel -1? What is the reason? What is the reason that I need to cancel the -1? Between -10 and -1, if we can cancel the -1 and just leave -10, the system itself is fast. The system itself is fast. It means if I leave -10 and I cancel -1, the locus will travel between these two poles. The locus will travel between these two poles. Maybe asymptote maybe at -5. Asymptote maybe at -5. But if I decide to cancel -10, if I use k s plus 10, if I use ks plus 10 and I cancel -10, our system gonna be, the asymptote will be between -1 and 0, which means the system gonna be slow. The system gonna be slow. So the trick for pole 0 cancellation is if possible, we will try to cancel dominant pole. Dominant pole gonna be the one that make the system slow. The one that make the system slow. In this case, between -10 and -1, the pole that is dominant and make the system slow is the -1. Here we have another question. Why we don't cancel the pole at 0 instead? Why we don't cancel the pole at 0 instead? The restriction, how to say, please keep in mind that don't try to apply pole 0 cancellation technique cannot be applied. No, shouldn't be applied. Pole 0 cancellation shouldn't be applied on unstable pole. The zero pole here on the paper, we know that it's exactly on 0, but in the real system, if we have the model uncertainty, 0 can be 0 plus or 0 minus. If it's 0 minus, of course, you are lucky. It's stable. But if you have 0 plus, but you cannot totally cancel it because in the controller, you model the controller by exact 0, but in the actual system it's the 0 plus, you still leave some component of the locus on the unstable region, which is very dangerous. So if the pole is 0, you should still keep it 0 in order to see how can we deal with that pole that near the imaginary axis, almost unstable. When it's 0, we cannot use pole 0 cancellation. When it's positive, also, if you have the pole somewhere here, you cannot directly put the 0 on it to have the pole 0 cancellation, because in the analytical way, you know the exact, you can predict the location of the pole, but in practical, it's impossible to find the exact position of the pole. You try to make complete pole 0 cancellation, but what you can see in the real system is if you slightly put the 0 here or slightly put the 0 here, it still have the dynamics of that. It still have the dynamics of that unstable pole, and the system still unstable if it have at least one pole on the right hand side of the S-plane, on the S-plane. So please keep in mind that you can apply the pole 0 cancellation technique only to the stable pole. Stable pole means the real part is negative. The real part is negative. Come back to our problem. We decide to cancel S plus 1 by the pole 0 cancellation technique. And now in the root locus, we only have P1 equal to 0, P2 equal to minus 10. And when we plot the root locus, again, we have 0 and minus 10. What is the asymptote of this root locus? Asymptote. The angle of the asymptote we have two poles and we have no 0. So the asymptote of this root locus gonna be 180 degree divided by 2 and minus 180 degree divided by 2. So we have positive 90, negative 90 degree. How about the intersection point of the asymptote? Summation pole subtract by summation 0 divided by n minus m. Summation pole gonna be minus 10. Summation free low is 0. We don't have 0. Divided by n minus m. So in this case, asymptote gonna be plus and minus 90 degree, and intersection gonna be at minus 5. The idea is the first pole move here, second pole move here when we increase the gain k, and then have the breakaway have the breakaway go up and go down. And what I should concern next is we need a fast system. We need a fast system. A fast system means the system needs to respond to unit step input and have 5% error with less than 3 seconds and without overshoot. What does it mean by? It means by the response to step input, a step input. They want the response to the step input to be have 5% error or the setting time 5%. The setting time 5% in less than 3 seconds. The setting time 5% in the chapter of transient response. In the chapter of transient response, the setting time is for 5%. 5%. The setting time 5% is 3 times of the time constant or 3 divided by sine omega n. Setting time 3 seconds. Setting time 3 seconds. It means we need sine omega n bigger than 1. In order to have setting time 5% less than 3 seconds, the sine omega n should be more than 1. Should be more than 1. When we come back to this root locus, sine omega n more than 1, it's just somewhere around here. It's just somewhere around here. Minus 1. It's still, it's still on the real axis. So the requirement of no overshoot is not a big deal because we still have damping ratio equal to 1 on the real axis. So what should be the gain K? In this case, the gain K, we may apply the concept of gain K equal to 1 per G per magnitude G of S0. S0 now is just minus 1. And transfer function now is this one. So we have magnitude of minus 1 multiplied by magnitude of minus 1 plus 10 divided by 200. Which means it should be 9 per 200. 9 per 200. K should be about 0.45 if nothing wrong. Wow, lucky. Okay. The analytical way is like this. You read the problem you try to apply the technique of pole zero cancellation from the PD control. You check the system need the time constant depending on the setting time, and you can know how fast in the system you need to design. And don't worry to confirm the damping ratio by the requirement of the overshoot. In this case, it's not difficult. We have only two real pole on 0 and -10. We find the asymptote and we can approximate the breakaway point, and we obtain the gain value by this magnitude. Because if we want to get the speed, we need to have the sine omega n bigger than 1, the magnitude of sine omega n bigger than 1. And at that point, the gain is about 0.045. By the MATLAB tool, I already applied the pole zero cancellation to this. So the open loop transfer function gonna be K multiplied by 200 divided by S plus 10. So num gonna be 200, and then gonna be convolution of S plus 0 and S plus 10. Again here I have convolution, right? The new command convolution. Now it seems like you have 3 possible ways to compose den. You can compose den by, you know that den is S squared plus 10S plus 0. You may compose den by 1, 10, 0. Or you may compose den by convolution of 1, 0 and 1, 10. You may also can compose den by poly of the root. The first root gonna be 0. The second root gonna be -10. You can compose den by these 3 ways, and we're gonna get the same result. And I plot the root locus of this open loop transfer function when we vary the gain K. And at this minus sine omega n equal to -1, which satisfy the speed requirement, the response speed requirement, we need the gain about 0.45. Agree with the analytical solution. And at this point, it's still along the real axis. So overshoot 0%. Then how can we obtain the step response plot to confirm that we achieve the speed requirement and the overshoot requirement? The gain 0.04 cross loop in order to plot the step response, in order to plot the step response, you need to use the closed loop transfer function. For the root locus, you plot the open loop transfer function. But in order to plot the step response to see the real response, you need to use the closed loop. I compose the closed loop by using the command feedback. And our sensor, the feedback is just only one. If the sensor has the transfer function, you need to, for example, it may be, for example, if we have 10s plus 1, for example, for the sensor, if you have 10s plus 1, in the feedback, you need to have 10-1 represent the sensor delay, For the feed forward, if you still remember the sys here, now the sys already combined the controller and the plant just leave the gain K. So when I already obtained the value of the gain K, I just multiply the gain K to the sys. Sys is this one. And how to say, feed forward. And here is sensor or the feedback. And I use the command names feedback to compose the closed loop transfer function. Actually, the closed loop transfer function here should be equal to K multiplied by 200 divided by S plus 10 and divide by 1 plus K. 200 divided by S plus 10 and gain K equal to 0.044x. It should be the same like this. It should be the same. And I just use the step 6. And when I use the step 6, we found that the time that it approached 5% of error. Actually, we want it to be faster than 3 seconds. But when we pick, here we pick the, when I pick the pole, the pole here is still less than 1, which means it's still slower than the requirement. You should pick the pole that higher than, you should pick something like minus 1 point something, and you get the gain K. And if you use that gain K, I believe that the setting time will be less than 3 seconds. And for this case, we don't have overshoot, which it makes sense because the pole is on the real axis, no vibration, no overshoot, and damping ratio is equal to 1, which it makes sense. Okay, I think that's all for today. A long day. Do you have any question? No question. I'm gonna stop recording the class. I will upload in Moodle later.